Okay, so number one, we've established K prime is 10 to the negative seventh in units or Tesla meters over amps. We have a small increment delta L in the I direction, and that increment contains the origin. So what is that? Well, if we just slop down an XYZ set of coordinate axes, and I've only labeled the X because it's the only one that's really important, our delta L is a small increment containing the origin in the I direction. So it's a little hard to write that very well with chalk, but the head of the arrow's on this, so it's an arrow going this way. And there's our delta L vector. Okay? Now we're trying to find the field at the point 1 centimeter, 2 centimeter, 3 centimeters. So, first thing we need to do, of course, we have our law. The I delta L is our current times our delta L increment. The R vector is what? It's the vector from our increment to the point at which we're trying to calculate the field. That's stated very clearly. The text states it very clearly. I believe I've stated it very clearly. And you have to know that. You have to know what that R vector is because it's the key to this whole thing. Okay, so the R vector goes from here to here. It goes from the increment to this point. And since the increment contains the origin, we're going to consider it's going to be a very small increment, as small as we want to make it. So we'll just take the R vector as being from the origin out to this point. Meaning the R vector is 1 centimeter times I plus 2 centimeters times J plus 3 centimeters times K. That should be relatively immediate. Okay, so we know what our R vector is. Our I vector is just our delta L vector, and our delta L vector is just delta L times I. Okay, it's a small increment. Delta L is its magnitude, and it's in the I direction. So delta L, I delta L equals I times delta L, the length of the vector, times the I vector. That's all we need to figure this out. So what do we get? Okay, well, I is 50 amps. So I delta L times I, big I, current, times delta L times the I unit vector is 50 amps times delta L times the I vector. So let's just go ahead and color code a few things. I've already used purple for this thing, so here's our I delta L. I'm going to circle that in purple, and I'm going to circle it down here just to be sure you see where it comes from. Our R vector, let's use a contrasting color here. Well, here's our R vector. It's this thing, okay? And of course we're going to take our R vector and divide by R. So well, it's very clear what the magnitude of R is. So, yeah, I'm not going to write it out. Our R over the magnitude of R, if we get the R vector, we can calculate R over the magnitude of R. Nobody at this stage should have any trouble doing that and seeing that this is it. Now these are all 14s because, of course, 1 squared plus 2 squared plus 3 squared is 14, not 13 as I tried to write down and people corrected me. Okay? So it's 14. So we just divide and of course, if we take these magnitudes, that'll be square root of 14 centimeters, right? So the centimeters are going to divide out, and this is what we're going to end up with. And that's, again, very, very clear. Okay. And then our denominator is the magnitude of R. Well, the magnitude of R, and I guess it's worth writing out the magnitude of R, is the square root of 14 centimeters. And of course, you can work that out, but that's going to be down here, and we're going to square it. So it's very straightforward. Once you've identified your I delta L vector, and once you've identified your R vector, it's very straightforward to write out this expression. Okay, well now we just multiply all the numbers. K prime is 10 to the negative 7th Tesla meters over amps. So we have 5 times 10 to the negative 7th Tesla meters over amps. Now, why didn't I write the amps down here? Because I'm also going to multiply that by our 50 amps. So the amps divide out, and 50 times 10 to the negative 7th is 5 times 10 to the negative 5th. And then I'm dividing by the square root of 14 centimeters squared. And the square root of 14 squared is 14, of course. And we get centimeters squared. A centimeter squared is 10 to the negative 4th meter squared. So here's our denominator. I shouldn't have to talk through all that. But I'm kind of talking through it to make sure I did it right, but I'm pretty sure I did. Okay. So now we've got delta L times I crossed with this vector. So the delta L I factor out. I do I crossed with this vector. I cross I is 0. I cross J is K. I cross J gives us K. And I cross K gives us negative J. Yeah, so we get a 2. Well, the I cross 2J is K, so we get 2K over the square root of 14. I cross K is negative J, so we get negative 3J over square root of 14. Now you can write this out with the determinant definition, but that's kind of overkill if you just understand the distributive, that you have a distributive law here, and know what I cross I cross J, and I cross K are, or can figure it out. You can immediately write this down without having to write out a whole determinant or something even worse. Well, we do this, and all I do from here to here is take that square root of 14 that's common here and put it down here. And then, of course, Tesla meters over meter squared times delta L. And I shouldn't have a arrow over that delta L, because I've already taken care of the vector nature by using I, dealing with the I. We have this. This is going to be Tesla over meters times delta L times this vector. And of course we can calculate that. But we can visualize where that is. That vector is negative 3J plus 2K. Okay, does that make sense? Vector in the direction of I plus 2J plus 3K. Okay, crossed with the vector in the direction of I. Our right-hand rule is going to be like this. It's going to work out. Okay, so that's the contribution to the magnetic field from this single increment, an illustration of how we use this rule and also how we think about it. We do want to think about where these vectors are and what it means to take the cross product, right-hand rule, and make sure that our vectors end up in all the right directions.